Hey, Leo.
Yeah, I don't think you know how to speak Latin or Greek if you think my name means catboy, but that's kind of
Well,
beside.
it's hyperbolic and rhetorical.
I'm just giving you shit.
What does it mean, though? Just so
what
everyone knows.
what mean? Leophilius?
Yep.
Well, Leo is, I believe, the Latin prefix referring to lion, or the Latin
Oh,
word referring to lion, and Filius is the from the Greek philios, which means lover of or to love. So it just means
gotcha.
lover of lions. And since I'm a Leo and the lion is my favorite animal, I chose to name Leophilius.
But you don't believe in astrology, right?
Astrology? No, I don't think astrology is an accurate way for understanding the world.
Okay. Uh, so yeah. So when you say a physical manifold, space-time, would you agree that physical things, the way we understand physical things, have physical properties such that we can call them physical things?
Yeah, if I'm understanding what you mean by physical properties correctly, then I would say yes.
Like you point to any physical object, a rock or a tree, to some
Mhm.
resolution. I mean, if we keep going in, we might see more things or the absence of things with like a massive microscope or whatever. I understand that it gets a little weird when you do zoom ins, but generally, you can kind of list some properties. You can describe the properties. You can even mess around with them. Like you can manipulate like wood fiber, let's say, or burn it and kind of see how it responds to certain things. So
Mhm.
when someone says, when you make the claim that space time is a physical manifold, what my brain goes to is, oh, physicality. Like what's physical mean? What does it mean, actual and concrete? Because to me, physical and concrete are synonymous. Are they?
I would
Maybe.
agree with that.
Okay, so if they're synonymous, wouldn't it make sense to go, well, what is it made of, right?
But you do know what concrete means, right?
Yeah, synonymous with physical.
Stands in causal relations. Something is
Okay.
concrete if it stands in space time stands in causal relations with things.
Well, I feel like that's kind of begging the question
How?
because we need space time to measure and to observe the causal relations of things.
Yeah. Don't you think that makes space time a real thing? Like,
No.
you do understand that we don't have to be able to perfectly describe something to know that it's real, right?
Yeah, real. There's real. To me, real means I permit a bunch in the term real. Like similarly, like laws of logic or something, or numbers, right? Like would you say laws of logic are required, or at least a precondition of just interacting with the world? We would say like, well, we can't just like not appeal to them to make sense of things or categories, and just kind of even talk to each other. We need to abide by some law, right, of thinking and speaking, right? And so but we wouldn't say just because that's required in reality that the laws of logic are actually physical. It would be that would be an illogical follow, right? Just
Yeah,
because we
I
need.
mean, I would say that the laws of logic are conceptual, but
Right.
I don't think that the laws of logic have degrees of freedom that in the way that space time does.
Right, but you're saying space time, because when you say space time, it's like this conjunction of space, the absence of matter, and time. In my view, the conceptual, it's like a tool to measure changes in what we're observing. Duration. It enables us to capture duration periods that we arbitrarily put like sort of numbers on. So when you say space time is in causal relation to reality, basically, right, to physical reality, when I say, well, space time, you need space time, the concept, to to even observe any causal relations, right? These things happen, we would say, in space and time, right?
Hmm.
So when we say, well, space time itself is physical, then if it is physical, then in what frame of reference, space and time, are we observing space and time? It seems like it goes to some meta um, point of reference, right? Do you understand what I'm pointing to? Like, if how do you observe space and time as a physical thing if the observing of space and time would necessitate another framework of space and time to observe that in, right? So in short, in what space and time do we observe space-time?
Well, we observe space-time by measuring the relations that it stands in with the material objects inside of it.
But wouldn't we just be measuring the material objects and using space and time as like a way to describe?
No, because what the material objects are and what they're doing has an effect on what space-time is and what its geometry is.
Right. So can you give an example of measuring the physical manifold of space-time, as you put it, directly?
Yeah, anytime you use the GPS on your phone.
The GPS is a man-made object that's interacting with another man-made object.
So if you do know, we have GPS satellites that are about 14,500 miles above the Earth. If we did not continuously readjust the clocks on our GPS satellites, within a 24-hour period, the GPS on your phone would be off by 7 miles. This is because the clocks on our GPS satellites literally, physically tick faster than clocks on Earth. We have to physically account for this for our technology to function properly. So time dilation couldn't be a physically manifested property if time weren't physical.
So you're saying time itself is a physical thing that makes clocks tick faster?
That makes, I don't understand that language.
What causes a clock to tick faster, which is a man-made object?
Well, what causes a clock to tick faster is it not being stressed by mass energy, it being outside of a gravitational field.
Okay, so the cause is in space-time. It would be other physical things imposing constraints.
On space-time, yes.
Well, on the object, because the clock you're referring to isn't space-time.
On the space-time that the object exists in. Space and time physically look different for different objects.
So what is the physical properties of space-time such that it can impact things?
Width, height,
length,
geometry.
Hold on. Length is physical?
Well, the broader term would just be the geometry of space-time.
Does it make sense that something's made out of length?
Made out, I don't see, it just depends on what you mean by made out of. That's somewhat of an ambiguous term.
Okay, wait. So if you said space-time is a physical manifold, and then we agree what physical means, right? I'm
concrete, yeah.
What is it made of? If I asked you well,
but I just don't think concrete means made of something. I think concrete means stands in causal relations. And so if space-time stands in causal relations with things, then it's concrete. And if by concrete you mean physical, then I don't see why you wouldn't conclude space-time is physical.
So do physical things need properties to call them physical?
Well, yes, but properties is fine. There are properties of space-time. We can measure its geometric curvature. We can measure its shear stress.
No,
we can
hold
measure
on. That's
length contraction and time dilation.
That's begging the question.
Well, what question is being begged there? Those are properties of space.
I said, what is it you're actually measuring, right? So if I say, what is
space-time?
Hold on. That's begging the question. What is space-time made out of such that it's physical? I
don't know what you mean when you say made out of.
If I can bend an object like a pencil or a rubber band or something, the reason I know I can do something to it and observe manipulation of the thing is because it's physical. I could know what it's made of such that I can manipulate it, right?
Mm-hmm.
So this doesn't seem to apply, from your view, to space-time.
You know, the pencil has a geometry if you bend it, you know. And you can describe the change in that geometry across the pencil.
Geometry isn't physical itself. It's a description. Right.
Yeah, the description of things. And the geometry of space-time is describing physical properties about a manifold.
Yeah, what's the manifold that it's made of, that such that it's similar to a pencil? Because it depends
Well,
if we say
I
wood,
don't know
right?
what you mean. I just don't know what you mean by made of there. That's just metaphysically ambiguous. I don't know what it is. When you say made of something, I don't know what particularly you might be trying to predicate about the thing that
let's
you're
try it.
speaking.
Let's do it one more time. Space-time. Do you agree? Space-time is a physical manifold.
Mm-hmm.
What is the physical manifold constructed of such that you can call it a physical manifold?
I'm just construct. It's just it's like asking what is temperature constructed of.
No. Temperature.
I don't know what that would
Hold
mean.
on. No. Temperature. You don't say is a physical thing. A physical
I
manifold.
do. Physicists do.
Wait, no. You can't grab temperature as a physical object.
Doesn't that yeah, but that's not what defines an object. You seem to think that physical means
Is an
like
inch physical?
constituted of some sort of like fundamental particle, but that's not what physical means. That's not what any physicist would say physical means.
Is an inch physical?
I really would depend on the context, to be completely honest.
Can I
mean, if you're talking about like an inch simplicator, I would say no. That's going to be a conceptual.
How about a minute?
Way. A minute? Well, a minute simplicator, I don't think so. No.
So you're saying, what about length?
Length simplicator, no.
So these things that are conceptual and arbitrary measurements, right, aren't identical to the thing they're measuring, right?
Of course not.
Okay.
I don't think I've ever claimed that, though.
No, well, saying temperature is physical is like saying temperature equals something physical, but temperature is our way of describing the heat in an arbitrary standard way of measuring heat. The heat and its absence.
What is heat made of?
Well, heat would. I mean, we're going to go down to what energy is, right? But we know
exactly. So heat and temperature aren't made of something.
We know
they emerge out of something more fundamental, right?
Okay, got it. But when you say we can say
the same
heat.
Be true for space-time.
Okay, hold on.
Most physicists think it probably is an emergent structure.
Okay, so if we know that temperature is our way of measuring heat or it's absent, right? It's just like a way we measure it. It could have been called something else. It could have been in different standards, right? But you agree that temperature isn't actually the physical thing that we're describing, right? It's not identical to it. It's a conceptual way to kind of measure and put in some place to know, well, what's the temperature of this water versus this water? Okay, so for instance, if we have two different buckets of water at different temperatures, right? We don't equate the water and the temperature as the same. Water, we know, is not made of temperature, correct?
Yeah, but temperature is a property of a water and is one way that we can know that water is physical, because there's a degree of freedom, a physical degree of freedom, a physical quantity that we can associate with it, correct?
I think we could know water's physical if we didn't have our ability to feel temperature.
So do I.
Right.
Because there's other degrees of freedom that we can describe about it.
Right. So there are other things about water such that we can list its properties, right?
Yeah, there are things about space-time that we can describe mathematically. We can quantify them physically in physical parameters and systems of equations that tell us how physical reality operates.
What would you say water's made of?
Water is made of, in at least the sense that I'm assuming you mean in this instance, is in like constructed of atoms.
And what,
or you could say molecules.
And we can isolate those and say, well, let's say mercury is not made of the same, right? Composed of the same exact things. We can know that.
I think mercury is a different element than oxygen and hydrogen.
Yeah, no, that's what I'm saying, is that we know enough about each of them separately that we don't just look at, like, let's say liquid mercury and go, that's water. We know enough. Right. Okay. So if we can make distinctions about water and mercury, what I'm simply asking you is, what's the distinction about space-time such that it's equal in a physical category as water and mercury?
The fact that we can describe different geometries in it and how those
geometry is not physical.
Well, no, the geometry isn't physical. The geometry is describing something physical. That's what I'm getting at. It's a degree of freedom possessed by a physical entity, namely space-time.
So are you just saying we don't really know what space-time is made of?
Well, the words made of are just a bit ambiguous here. I think most physicists would say it's going to depend on what you mean by made of. If you mean by like made of a particle of some sort, space-time probably isn't made of like a particle of some sort. But the idea that being physical isn't defined of being made of like some particle or something like that. A physicist is going to say something's physical if there are independent degrees of freedom that we can objectively quantify about that system. And we can with space-time.
Can you say what you mean
with a star or a planet?
Can you say? Can you clarify what you mean by freedom there?
Like a degree of freedom is just the fundamental physical parameters defining the state of a system and its evolution through time.
Okay, so you would say that for any other thing that we're witnessing, you would need space and time as sort of a reference point to observe any other changes. Let's say something was bending, like a tree was bending in time from maybe the wind or something like that. We would look at the tree and go, the tree is not the wind. The tree is not identical to the earth it's in and on, but it's a thing that we can observe. And we see this thing in time, right? Through a duration bending, maybe it eventually snaps or something. So you would agree that space and time, I'm not saying space and time is the same as space-time. I know there's a slight distinction in how you describe those things, but you would need space and time as a way to even describe mathematically what was happening with the tree, or even in natural language, what's happening with the tree, right?
In a sense, yes. But something that relates to what you're talking about is a difference between sort of what space and time are in the Newtonian sense and what they are in the Einsteinian sense. So even like people like Newton and Galileo had a concept of space and time, but they would have probably thought they were this sort of like immaterial, immutable sort of like backdrop against which things are measured. That's not what space-time is in the Einsteinian sense. And it was a result of a variety of measurements that we made and physical models that we developed that we figured out space-time is, in fact, a physical thing that can be directly affected by things inside of it.
So so the thing you're referencing is that mass impacts space-time, but then it's mutual. Is it also space-time bends in response to mass? And that's kind of like what generally you're stating here?
Sort of, yeah.
Okay, so if we say space-time is bending, look, right? And go, oh, look, it's bending. My question is, in what reference point? Like, what are we using? Inside what framework are we using to look at something called space-time and go, look, it's bending? And then my other question is still the same. What is actually bending such that you know it's bending? Right? That's, like, what is it that's bending? Because to me, it seems like a kind of a poetic way to describe how things exist in space and how.
I would agree with that. Bending is not really the right way to think about it.
Okay, because some people, like different people, actually say, no, it's physically bending. We know that physically. And this is why I'm trying to get less ambiguous with the terms. Maybe the term space-time and its physicality, in the way it's claimed to be physical, is just kind of like a result of not having another word to describe it or put a category in it. Because to me, space and time, separate as concepts, but even the conjoining of them in a concept seems to be something that can't ever exist independent of itself. So it's like self, you know what I mean? Like, in what time and space are we looking at space-time? There must be another framework, right?
We don't need
such a thing.
We don't need to. We can just look at the effects that we see in space-time.
Right, but how do you
and the reason that we know it's space-time that we're looking at is because it's lengths that are contracting and it's times that are dilating.
But I'm saying, if bending of space-time itself is an effect, inside of what framework is it an effect of?
Space-time. Space-time is what's being geometrically curved by mass energy.
Right. You're saying space-time is being curved by mass energy, and I'm saying, in what space-time are you viewing that?
I don't understand what I really don't understand what that means. It seems to me that you think there has to be some sort of like meta space in which we're looking at our own space-time. That's just not the case.
Well,
We
I would
can
say,
observe our space-time curve. We can do it literally with optical telescopes. We have.
well, I'm saying for anything else that we say curves or bends or does anything, right? That like physically as an action, like it's doing something. The concept of something doing something, the only way to observe doing something is in time and in space together. You need the two as a sort
Not
of like
necessarily. There
that
are
you don't-
physical models where we don't need that to describe certain physical behaviors.
you
One
can,
of those is, in fact, ADS-CFT correspondence, where space-time is an emergent structure below which we can still certainly describe physical aspects of reality, but we don't need space-time to do it.
well, the fact you're doing something means you're in space and time.
Not necessarily. Well, in virtue of what?
Being just observing, being an observer requires
Yeah, but
space
in
and time.
virtue of what does observing require space-time?
Well, observing something means you're observing the external world, and if you're
Yeah, I'm just not understanding why this necessitates space-time.
well, I don't think anything necessitates the conjoined term space-time. I think space and time, right? Space-time and matter as a continuum are all necessary preconditions for observing anything going on.
I don't think so.
So what's one
Certainly
thing
not matter. There are things we can observe that aren't made of matter. They make up matter, but they're not made of matter.
No, observe anything. One of them, one or all three are in play. Like there's nothing you can observe that's not in time that you're observing it.
Well, technically, it just depends, because I mean there are dimensionless quantities in pretty much all of our physical theories. That meaning that these quantities really just don't really exist in space. They're dimensionless. But yeah, there's nothing in physics that mandates we need space-time to give physical degrees of freedom for a physical system and describe its evolution.
Well, evolution would assume time, progress.
Well, if you're looking
duration.
at certain levels of evolution, yeah, but
I don't think you could
information theoretic senses. You don't necessarily.
Are you saying that there's something you can observe that doesn't, that in the action of observing it doesn't assume duration?
Yeah, there are probably certain things that don't, that the concept of duration probably, like entanglement, that there's no duration to entanglement.
That's like particle entanglement?
Yeah, quantum entanglement is.
Okay, but that's a theoretical descriptor. I mean, do you observe it directly?
Yeah. Yes.
Okay, so how do you observe that without a duration in which to observe it?
Because there is no duration. There's just the quantum states, and then you measure the quantum state. When you measure it, you get information about all the other states that this state is entangled with, because you can't describe them separately. There's no time. You don't really need time. We don't really know the role that time even plays at the quantum mechanical level of reality.
Right. Okay. I mean, that part's theoretical. We're not sure something about a larger lens of how we're viewing this stuff when we're talking about quantum stuff. But it seems to me that there's no way to escape. Like if you say, oh, we observed something in quantum entanglement, and then you go, okay, who was it? Was it Leo? Let's say you did it. You like look through something, maybe some machine or modeling software connected to something. You are in fact in time observing a phenomenon, right?
Well, I am, yeah, but that's not all measurements have to be constructed that way.
Okay. So I guess my question is kind of back to the start, and I won't exhaust either of us if we can't like get to a crux here. Is that people, and again, you at least admitted, not that it's like a loss in any way. It's just that some people refer to bending as like a physical thing that's occurring with a physical thing, a thingness called space-time. And you're saying it's not quite the case, that the thingness we're talking about called space-time is it's like a physical thing, the way I would say a pizza is a thing, or the way they would describe it on all the videos where they drop the bowling ball right in the fabric, right? There's no other way, that because
that's just an intuitive sort of depiction that
right.
That's only two-dimensional. It doesn't really capture.
But people say fabric, right?
Yeah, people say fabric. That's again.
Also
see, this
limited.
is we're limited by our language. You know.
Okay, that's fine. So, but if we are limited by our language, that's totally fine, because then I can look at this as like a conceptual way to perceive objects in space and how they relate. But once you say there's some causal effect, which I think you're also saying, which I think the two aren't, I don't think they go quite together. Like if you say, well, it's a conceptual way that's limited by language, but also there's a causal, we know
certain descriptions of it are conceptual and limited by language. But what it is that we're describing is certainly an objectively real thing.
Right. And so when you say it's concrete, physical, like in synonymous, right? You're also saying not all concrete things are physical.
Well, I mean, what I was saying is that if we both agree that physical and concrete can be used synonymously, that I just take what most metaphysicians would define concrete as being separate from abstract, and that's just things which something is concrete if it stands in causal relations with other things.
Okay.
And space-time does stand in causal relations with other things. So if that's what we understand concrete to mean, and we both also understand concrete and physical to be synonymous, and space-time satisfies that, then I just don't know why we wouldn't agree that space-time is physical.
Well, I mean, I could say, I wouldn't skip to physical, because again, to call something physical, in a sense, the same, you know, the example I used with the difference between, in other words, we can establish identity of physical things by interacting with them directly, such that we know the difference between water, not just visually.
We can do that with space-time too.
Yeah, but how do you interact with the concept of space-time as a physical thing?
Space-time isn't a concept. We can interact with it by manipulating its geometry. We can see this all the time in gravity and gravitational experiments.
Okay, so give me an example where you're manipulating the space-time with an object.
Within an object, I don't.
No, with an object, because you said we can manipulate space-time.
We use. Well, we're not really the ones doing the manipulating. We're just taking advantage of the manipulating, such as the event, the how light is distorted as it moves through gravitational fields.
Okay,
it's a physical thing we can see. If space-time is, obviously light is a physical thing. Maybe you do disagree with that. I would imagine you don't. Light is a physical thing. I mean, I can literally look at it's kind of hurting my eyes. I'm looking into the light bulb. I can see it's bright. Light is. Would you agree that light is physical?
I'm not sure we know exactly what light is. I think light has different can emerge from different states. And
light is very well defined.
Well, I'm saying light is almost like, in a way, synonymous with energy or something.
By the way, I'm still listening.
That's fine, thanks.
This is sort of another tangent. We don't have to go down this road if you don't want to, but light is electromagnetic radiation is actually almost completely defined. That's one of the most fundamental things that we have. Well, it was the attempts to really quantify what electromagnetism was that gave us something. This is probably a term I'm sure you've heard of before, that gave us gauge theory, which is utilized in particle physics to help describe the three fundamental interactions. Those three fundamental interactions, or more specifically the gauge theories that describe them, are probably the three most complete physical theories humans have ever developed.
Right. I think you'd reserve some percent of saying light is absolutely well defined to the extent it's like a settled thing, because of how it's still a little bit mysterious in the way it emerges in different scenarios. But we don't have to get into too much of that. But the other thing about light, not to go on a tangent, but it's just interesting, is that I think we've gone back and forth in the chat about this, is that when you're looking at something, you're never observing the light directly. You're observing what is referred to as light reflecting on things. But then
it's still light. It's still photons.
Right, but you're never observing that directly. You're observing a reflection.
You mean the object. You're not observing the electron. You're observing the photon that's scattered off of it. Is that kind of what you're saying?
Well, no, I would even take it further that what you just described is you're actually observing the object, the physical object that's reflecting something. So you go, oh, look at that light. and you're really saying, look at the thing that's reflecting this other thing, such that it's seeable, right? But then there's these examples. I don't know if you've seen this, but I saw an example of someone shooting a laser through like a contained like a glass sorry, the vacuum chamber, sorry. The vacuum chamber, and they had particles in there and air in there, and it was like, you see this really sharp laser, and then you go, you hit the switch and you try to get it to a near vacuum, and you no longer see the light, but you know that it's going through because you can see the green on one side, and then also on the other side, it's hitting an object on the other side, but you don't see the stream anymore. So, I mean, that also shows, not in every sense or example, but it does show that there is light, what we call light, going through something, but we don't even see the light itself, but we do see where it reflects. So that means like there's a bunch of light that we don't see all the time.
What is it that's reflecting?
What's it reflecting?
What is it that's reflecting?
Oh, off of the thing? Yeah. I'm not certain I think what you said, theoretically,
electromagnetic radiation.
You'd call it photons, because radiation would be just a category, and then you'd have to get smaller and high.
Right? Technically, yes, but that's why I specify electromagnetic radiation. Because I mean, you are correct there. The radiation is a broader category, and there's different.
But you'd say, what did you say? Photons.
Photons,
but
particles of light.
Right, yeah, particles. But then you don't. But again, we agree you don't observe them directly, but you would observe an interaction between what we call that stream, whatever pulse of energy going through, and then it hits something. And so we're always observing the thing that it's interacting with, and we just, naturally we call it that. Like if I go look at the light, everyone will know what we're talking about, right? We'll look at the light. It would be silly for me to go, you're not actually looking at the light. I don't know why you refer to it that way. It would be really annoying if I did that all the time. But we know that when you look at even the thing you said was blinding you, you're not looking directly at the molecular source of light, but you're looking at something that is
light
medium.
Is smaller than molecules. Light is much smaller.
So we agree we don't observe light actually.
Depends on what you mean. Your eyes are actually physically interacting with photons. That's how you see. So if one considers photons light, and I do, light, electromagnetic radiation is nothing over and above the propagation of energy through the electromagnetic field, which is deposited on other physical objects in discrete chunks that we call photons. And if you think that's what light is, then yes, we do see the light. We are interacting with the light. If you think light is something over and above that, then perhaps maybe, but then that's just going to be more of like more of a metaphysical disagreement.
Well, I mean, you would agree that there's light that we don't see, even that just
doesn't. But there are frequencies of electromagnetic radiation that do not interact with the particular cells that we have in our eyes, because they don't interact with photons that are either above or below a certain energy level. Yes.
Right. So what are we saying? Because I guess we can shift from space-time, because I mean, I think we've exhausted. I don't think we'll agree on what's being asked and what I'm demanding of. But
I do want to say one thing on that, not like to disparage you or anything like that, but I do think the questions you're asking are meaningful, and I do think that you are being honest with asking the questions. I don't think that you're trying to troll. I think these are things that you're genuinely curious about. There might be names you already know, but I would very much encourage you to look into the philosophy of physics, because some of the questions you're asking have actually been asked by some of the biggest brains in physics and in the philosophy of physics. What is the nature of space and time? All these, so like the questions you're asking are not like super far off par, if you know what I mean.
No, I understand. Yeah. The reason I asked them is because I'm obviously using my own brain just to go, wait a second, what is actually meant when because they always do the bowling ball and the fabric, and everyone's sort of mesmerized and they get a concept and a visual. But then I go, well, it's not exactly honest. It's analogous. But and then people say the fabric, I'm just simply going, well, what is physical such that it's bendable? But then you get different varieties of explanations. They go, well, I've heard people super smart, way smarter than me go, well, no, Jimbob, it's not, it doesn't actually mean causally physical. It's a way to describe this relationship between object and space, and then our way to make sense of the perception of time that would change depending on where you are. And that makes more sense to me, because if, let's say, you experienced some big bomb or something near you, right? Like like someone used an M80 or something really loud, and then I was like 50 miles far enough away where it was delayed, right? But I can still hear it moments after. Like, I look at that example, and I don't look at that I'm experiencing the past, right? I go, okay, Leo just texted me and he said, dude, this crazy sound went off. Did you hear it? And I go, not yet. And I don't refer to the thing I will eventually hear, a sound wave finally traveling and hitting my ears. I don't see that as I'm seeing the past or anything, right? Or you experience the present before me. What I would see that as is, given some distance, we both experience the exact moment at different distances. And so the further distance I am from the explosion, I'm actually experiencing exactly what I should experience at that distance away from the explosion, right? It's not that I like missed out on a different reference point, because it would just, you know what I mean? Like, it's not, but sometimes I hear people describe that as like, no, we're actually experiencing the past. It's finally made it to us, right? And I wouldn't say that. I would say that's the present in two different places. Do you know what I mean? And this is, to me, I relate this to time itself, because our perception of time could very well alter completely, right, between two different distances of the same event. But I don't see how that follows that, like, suddenly there's this thing that we can bend and morph space time. It might be a different example, though. Maybe I might be going too far into the theoretical example.
The thing is, there are universities that teach courses called philosophy of space-time or the philosophy of relativity. I would say, and I think that the overwhelming majority of both physicists and philosophers of physics would agree that space-time is a physical thing, but I don't think we need to fundamentally understand what space-time is, because I don't think we do. There's a lot of things out there I don't think that we really have a full grasp on. But I don't think we need to have that in order to say that something is physical. I think the fact that there are parameters associated with space-time, that it has a metric that can be used to make predictions, that things inside of it can be affected by it, that it has a geometry that we are capable of quantifying. I would say that these are enough to classify space-time as some sort of physical object. Sure, we might not know what it is. I mean, we go back 3,000 years, no human knew what, like, iron was made of. But that doesn't mean it wasn't physical. That doesn't mean there weren't other ways that they could interact with it and understand it and describe it and make predictions about things and what have you, that still tell us that, hey, we might not really understand fundamentally what this thing is, but we are capable of understanding it's a physical thing. We can describe it. We can interact with it. It makes predictions. It affects other physical objects. It stands in causal relations. And I think that's all that needs to be necessary for establishing that something is physical. But it could just be the case that me and you have different intuitions about what it means for something to be physical, and that's not necessarily a bad thing.
Right. And because also, like, the emergence of, like, quantum stuff, we're still at the point where quantum and relativity don't mash together well mathematically, right? And so they're trying to find a unifying thing to make them go together, but they don't go together. It's like a bad sandwich with two different sides. So, I mean, the reason this makes sense to still be in question of it is, obviously I have a different, demand for what it means to be physical, such that you can say something's bending. I'm like, I want to know what's bending. And then really all I get is it's space-time that's bending. And that, I guess that's as furthest we can take it. But I do wonder how they're going to kind of go forward, being that quantum and is at least the more it's getting popular. Let's say I can't
ask you a quick question, Jimbob?
Yeah.
Just out of my own curiosity, do you think that space-time is a real but non-physical thing, or do you think it's just a conceptual tool?
I think space and time, it's the only way I'm able to get to something that's the two together, is I look at space and I go, okay, there's dimension in the absence of matter we can call space, but is there ever an absence of matter at all? Really, I don't know. I don't know what a pure vacuum actually is. But let's say
That would be true in physics, because even a pure vacuum does have fleeting,
right.
waves from the quantum field still in it. So
Right. So I guess natural language, we go space. It's the absence of matter, like, but it includes something you can't see, probably. I could accept that. And then time, I just look at like, well, time is a necessary, like, again, us calling time what it is. We're never referring to something that we're actually seeing. We just go, we're in time. The moment we try to like isolate it, it's fleeting, it's ongoing. And so to me, it's, I actually don't know how to refer to it because I don't see it as a physical thing. But then when we talk about time as far as using it as a way to measure things, people say, and I want to get your take on this, because I get like in a colloquial sense to say, oh, we measure time all the time. And I think more rigorous about that. And I go, wait, isn't it more true that we use time to measure? Like, we're never like, I'm going to measure that time over there. We say, oh, here's this thing. We have time. It's always going, right? But what we're actually measuring are snippets of duration or intervals, and we get to number those things arbitrarily. We came up with a decent number system, right? That goes down to the microseconds or whatever. So when you ask what time is, I think it's like a way to measure changes that we observe in space, such that it makes sense to us, that like suddenly observation is possible. So I see time and space is more like some sort of precondition, along with obviously logic and math and language and stuff, and being able to see for the most part, to make sense of the external world. But I don't look at time as something I can ever point to in any given moment and say, see, that's it over there. To me, there's no it to time. So it might be just my mistake of assuming those things as I know them to be and going, what are they doing? They're smashing them together. Like, is space time, the joining of space and time? In my view, there's nothing there physically, right? There's nothing there. But I would also say that both are a part of our physical experience, just like language and meaning. But I wouldn't say there's a physical thing called meaning we can touch. So I would put time in like any other category of measurement, but I would probably include it in some sort of metaphysics in a way, like meaning. Like I wouldn't say meaning. I would never, if someone said, oh, we're bending meaning, and I would go, okay, in a sense, I understand you're twisting meaning or something, but I would never assume a causal thing called
that
bending.
there's like a physical thing being bent or twisted.
Right. And so I can't get myself to think of time in the way that's presented in space-time, that there's something physical being bent itself. And then
I can sympathize with that, because well, I personally would say that space and time are physical. They aren't physical the way that, say, this Bic lighter is physical, where if I bent it, you see it. And that's why I personally don't use terms like twisting and bending and warping when it comes to space-time. Those are I often say that's the terminology that is used to like explain it to like a middle schooler, that helps them. Same with the bowling ball and the trampoline. That's just a way to help conceptualize, because everybody knows you put a bowling ball on a trampoline and put a marble on it, the marble rolls to the bowling ball. And it is for similar reasons that objects are attracted to each other in space-time, but that doesn't really fully capture it. That's why I just choose to use the term geometric curvature. There's a geometry to space-time, and what that means is that we can describe it utilizing the mathematics of geometry. We can ascribe a geometry to this thing, and we can observe changes in that geometric structure as a result of the presence of mass energy.
Okay, wait a second.
Where
right there,
you get differential geometry from,
so,
because you have changes going on.
I got it. So okay, but the thing you're pointing out there, let's say in this case you're looking through space and you're seeing that light's bending, and objects, something's changed, something's occurring in a way that there's let's say curvature, right? Or something like that.
Cleansing.
Some sort of, right. Okay. So I guess would you consider that like, that it's assumption, and it might be reasonable even from someone's view to watch objects doing something, but then make a claim that it must be the things in that the objects encapsulate that's doing the thing. So you know what I mean? Like the difference between objects doing things in space versus this concept, like I think usually in like YouTube they show like the raisin bread expanding, right? Have you seen that? That's like a visual way to describe something expanding and maybe morphing or whatever. But to me, maybe that's like where I don't take the leap, where I go, well, you could observe something, and from your point of view, something could be altering and bending, and in any direction you could view this and you could go, wow, we're really watching something occur here. But then assuming the bread, right, as opposed to what just raisins are doing, we're assuming the bread, there must be a bread thing, right? There must be some other thing that we're not seeing directly that's doing this thing, because we're looking at the particles inside the thing. And it would be just, we couldn't possibly explain it any other way, that all of these things move similarly in this space thing. So maybe that's the jump that's being made, and maybe that's why it makes sense to a lot of people to go, oh, look at all these things, light, objects moving in a certain way consistently, and maybe even you look at something that doesn't move consistently and you go, whoa, what the hell happened there? That was irregular or something like that. That must mean something influenced it. But the problem, I think, in astronomy and cosmology is it's impossible, as far as at least now, to like get in there and manipulate anything, to like remove anything, and we just don't have access to it. And I think it's probably annoying to most people, because you have to resort to theoretical explanations and descriptions, which are useful, but I don't think explaining something mathematically even if it's coherent and can predict, I don't think mathematics can explain actual phenomenon happening without any interaction directly, right? And so I think that's.
I would agree, and that's why I would say if we've got mathematical descriptions that can make predictions and that do describe things, then there's probably some sort of physical phenomena going on there. I think most physicists would say that, even if we don't fully understand the nature of that physical phenomena, because it's just non-intuitive. It's not like there's just a math, but absolutely nothing below it. The math is describing something. We might not fully understand what that something is. It might be beyond, our current technological capability to fully understand, but there's definitely something. And that's the difference between physics, which is very much an applied mathematics, and pure mathematics. So in pure mathematics, you're not really describing anything. Oh, I mean, you are in the sense of describing further structure in mathematics, but I mean, in the sense that I think that we're both talking here, you're not really describing something. But in physics, you are. There's something. It's not like we just make up a bunch of math and say, well, I guess this is what we're going to run with. It's that we hone in on the math that describes what it is that we're looking at and what it is that we're talking about to make predictions to understand reality. And that math is definitely going to be describing something.
But you would agree wrong models could accurately predict correct things?
I think yes, but not in as strongly a corroborative way as we see from our current physical models.
Right, but like if like we accurately described a phenomenon, so long as we had access to viewing this thing in some decent chunk at least, such that we could make predictions merely because the repetition of behavior, we get mathematical and describe that to some high level of detail. Maybe there's a margin of error, but then if we assume a cause of some behavior that's predictable on its own, in other words, you can predict behavior of the external world so long as you have enough time to kind of like isolate what's happening, and as long as it repeats, you can go, wow, that's predictable, and then you could mathematically describe it. But then I think what happens, this is a question if this is possible. I think it is, and I think it happens, is that then you incorporate another variable that you assume to be the cause, and if you can describe that new variable inside your math, include it, and it still predicts, there seems to be this kind of like, at least in the last 100 years, this sort of like near blind acceptance to go, well, yeah, I mean, their math that included this new hunch of something causing it, the math checks out. So therefore, we have no reason to, question it. Maybe not. I guess question is a little too big of a statement. More like, it makes sense. You know what I mean? Like, you just kind of go, well, it makes sense. They basically, you could reify a cause for something and then take what's predictable, and you could make you can make math work, including this new variable that you're calling your cause. And then you can go, see, guys, I created a cause and I put it in the math, and it still works out such that it's predictable. And I see a lot of people online in sort of the debate channels saying that's proof. And I would say, it's maybe indicative at best, but I wouldn't call it proof in the sense when we use a scientific experiment where we could actually manipulate. And I think, again, if we're talking about space and stuff, I think this is the biggest problem that everybody doesn't like, is that you can't manipulate the thing that you're assuming might be causal out there, right? We're very stuck to our local experience for the most part.
But we have that all the time in physics, don't we? I mean, where we don't really have the ability to manipulate physical systems, but we can still describe the ways in which they interact with their environment and derive, get predictions about how things are going to play out. Like, if these things interact in this way, we should expect to see this. When we go out and we see this, and we're like, all right, that's a point in favor. That's a point in favor of the model. I think that's all that's being done with the mathematics. For instance, Paul Dirac. I mean, when he developed the Dirac equation, what he realized is that in order for it to actually meaningfully describe physical systems, he had to add in an extra sign, a negative sign, and what that immediately implicated was the existence of antimatter. But that wasn't a thing that anybody had observed. It was kind of wondered, well, is that really a thing? Like, there a lot of the time, actually, in physics, there will be things implicated by the equations, but the physicists are like, no, I mean, we don't really. I mean, the math says that it's there. We don't really know. It maybe, probably, and then. But the thing is that, like in the instance of dark or antimatter, I mean, we do have observed dark matter indirectly, but in the instance of antimatter, we ended up actually finding it. So, and that seems to have been the case. I mean, with general relativity, gravitational waves were predicted. We discovered those. Black holes were predicted. We discovered those. The expansion of space-time was predicted. We discovered that. I should say the expansion of space was predicted. We discovered that.
Wasn't dark matter or matter of color like not discovered, but assumed because the previous concept that included the Hubble's description of an expansion and what you would need to be observing as far as energy, and then they said they needed more energy. Like, wouldn't that be
that would be dark energy?
Dark energy. Okay. So, but that
dark matter was galaxy rotations.
But when you say dark energy is more close to the thing you just said, where it was like, it's kind of.
Well, there is definitely extra energy there. We just don't really know what it is. It's probably just the energy intrinsic to space-time.
But isn't that a necessary, like it's an argument from necessity? Like it be given...
Well, kind of, yeah. I mean, there has to be, in order to get the universe that we see, there has to be some extra energy beyond just the baryonic mass.
Okay. Here's a little...
and the electromagnetic radiation and neutrinos.
Okay. Is it the case that there has to be that energy because of what we see, or is it more accurate to say there has to be that energy because of the way we currently describe what we see?
Both.
But those could be not the same, though, right? They might be the same, but they could be different.
I don't think our mathematical descriptions. I mean, you could get different descriptions of reality that are mathematical, but the ways in which mathematics is going to differ and still reproduce the reality that we see is going to be like. It's not going to preclude any of the conclusions that our current physical theories have reached. Mm-hmm. You don't get a flat expanding space-time if 69% of the energy density of the universe isn't this some sort of energy. We don't really know what it is. If there's nothing there, you don't get the kind of universe that we see.
Right,
Kind of like if you didn't have somebody build a house, you're not going to get a house. So if you see a house, you know necessarily somebody built it. Same basic principle.
I get the example, but I think the difference is we know exactly how a house is built, and we can there's like a specific way.
You don't need to know how the house is built to know that if you see a house, it was built. You could just say, I have no idea anything about construction or how it was built. But you still know that it was built because there's a house there.
Right. Yeah. I think that I think the world has to be, at least locally, the world has to be a certain way for us to build a house such that we can be informed, well, that was built or whatever, because we don't just see them grow, right? But I think when we talk about the universe, right, as this is another thing that I think is kind of a problem in astronomy and cosmology, is that we refer to the universe like a singular thing, which assumes some sort of finiteness, doesn't it? If it is a the.
I don't think necessarily. That gets into just more sort of language games between physics and perhaps non-physicists.
I guess what I'm saying is, to make it not a language game, to call something an it, there has to be a not it. And so the question is, if there's this universe that's ever expanding, but it's also infinite, then the question is, well, what's expanding and into what, such that it's not the it, right? So there's a space. So that thinking about like the universe as something that's complete, then it suddenly necessitates some larger universe that it's inside of. And so is it ever this is my kind of arguments against kind of metaversal concepts and simulation stuff, is that the moment we discern something that, at least in the process we're doing, we're trying to discern something that's outside of this thing we call the universe. But it seems that the moment you discern it in any given way, observation, measurement, or whatever, the moment you do that, it's now a part of this. It's almost like you pulled it into this universe, right? And so it seems like every time we explore outward and assume there's something that's not this, the moment we see it and understand it or try to understand it, it's suddenly now a part of it. You know what I mean? Like visually, it would be like everything we know and all knowledge is one circle, right, of the external world, including the universe. And then we assume, well, there's something outside. And then the moment they overlap, they sort of become the same thing. And it seems like that alone, to me, that shows some problems in this kind of like the way we refer to it. Yeah, I'm being picky with words, but I think this is why I get in so much confusion with this particular category of knowledge, is that it's, again, I understand it's limited to analogous knowledge, but at the same time, we are referring to things, right? Like the universe is a reference to a thing. And if all these other people are assuming, well, there might be multiple universes, then to even claim that, you would have to kind of know what a universe was as its own thing, right? And I don't think
I think the concept of a multiverse is metaphysically incoherent, personally. Kind of for that reason, like what does it mean to say multiverse? Like, either the whole thing that each of these like, if all you're saying is that universes, not like but the whatever the word is, are saying is that, well, universes are just kind of like galaxies are, like what universes are to this meta space is what galaxies are to our space-time. Well, then that whole meta space is just a universe. Like, what? I don't.
Right.
But with respect to the expansion of space-time, what's expanding is the scale in space-time, and it's not expanding into anything because it's not like the universe is an object getting bigger in some otherwise pre-existing space. It's a intrinsic metric expansion of the scale in space-time that is measured over sufficient enough distances.
So when Hubble created the sort of visual balloon skin, let's say, around it, like he was making an arbitrary endpoint, right? Like it wasn't like we're watching this thing expand because we know what it is. He's taking a reference that he can see and creating an arbitrary boundary that's not actually there necessarily, but a boundary, and going, okay, from this point, we're trying to describe outward expansion of basically the observation of light, right? Just generally speaking.
Sort of. So there are galaxies that are very, very distant from us, and the emission spectra of these galaxies is shifted in one direction, and the further away they are, the more shifted in that direction it is. So we know that shift in their emission spectra is a function of their distance, and it's the shift is towards would be towards the lower energy end of the electromagnetic spectrum. What this means is something is causing the electromagnetic radiation emitted from these galaxies to dissipate more quickly than it otherwise should, in a way that looks exactly like what we would expect to see if space were expanding.
Okay, so those two, one could be right and the other couldn't be, but one could be right and indicate that the other is right. But it doesn't mean they're both right, but you're saying that the observation and the framework of the description of the observation matches this other thing that's also based on some framework.
I mean, almost perfectly matches.
Right. Okay. Yeah, that stuff is I
mean, if you woke up and you looked out a window and you saw things moving by in one direction, the closer they were to you, the faster they were moving, but as it got further out, the slower they were moving. You would assume you're in some sort of vehicle that's moving, right? Like that would be your immediate assumption, is that you're moving in some sort of vehicle past a bunch of stuff, like trees or something.
Maybe, yeah, possibly. But because I know, being at a stoplight, I thought I was moving and a car was actually moving. I thought I was rolling backwards and the car was actually moving forward, and I thought I was moving. So
you think it's possible that a whole forest could just be wishing, or just wish past you?
I think it's possible,
rather than that you're moving. I mean, I think it's possible, but
yeah,
I think which is a more parsimonious explanation, that you're in some vehicle moving through a forest, or that a forest is wishing past you?
Because of what we know of forests and vehicles, that would be easier. But because
because of what we know about galaxies, this is when we see this, the immediate assumption, okay, so space is expanding.
No, because I think because
is there a better explanation?
Well, if we take the position that there's no static reference point, right, that it's all where you are, right, depends on where you are, what's actually happening. And then if that's relative, if it's relative, then any assumption we have about describing what is the case in the sense, because the example you gave, we know, relatively we're stationary as humans standing somewhere, right, at our window in this case, and that from that position we don't sense ourselves moving, so we go, okay, it's obvious that what you said is likely the case with like cars or trees moving around you. But when we get into space as we see it, there's no other example we have access to, right, of another sort of universe that we observe in another particular way from a static reference point. And so it's quite possible and admitted by previous astronomers that there's no real way of getting to the bottom of it, because of the assumption of no true motionless observation point. And so if everything's moving, then you're really only describing what might be the case from where you are. But the fact that you're always moving and everything else is moving, there's not like a perch, right? Like a perch to go, this is likely it. So it could be the case, given that we don't have access to other universes, right? That everything we're seeing is moving together in uniformity, right? But we can't. There's no way to have access to the vantage point, right? If relativity is true, there is no vantage point, right? Actually, there's a theoretical vantage point, but wouldn't you have to wouldn't you have to admit that there would be no actual reference point?
We don't need a reference point to observe expansion. We would observe expansion from any point in the universe.
Right. So no matter where you are, it would be the case that it would
yeah, which is another reason why we think space is expanding, is that you would observe this from any point in space.
But have we been to any point in space?
I mean, in the orbit of the Earth, yes.
Right, but we don't know that exactly. If it's true what you're saying, then the consequence would be in any point in space, it would look the same. But we don't have any point in space. We don't have access to any point in space.
Well, we can look at cosmic microwave background, and that kind of shows us that
right, but our position, though, we're talking about physical position.
Yeah, but how we would get out of our position to know that the universe looks kind of the same other places would be to look at the cosmic microwave background.
Yeah, I think that would be a jump as far as knowing what you would observe, especially considering you assume a universe that's always bending things in light. And so there might be some other vantage point where suddenly we realize, holy shit, the way light
we can
bends,
account for that bending in the cosmic microwave background, the integrated Sachs-Wolf effect.
No, I'm saying, is it possible that some far distant position in the universe, the appearance of expansion may very well not even be consistent with our position here? Is it possible?
I don't think so, no. Logically, I mean, I don't really know. I'd have to sit and think about it, but I don't know what it would mean to say that we observe a galaxy, you know, we observe that its emission spectra is redshifted, and that is directly proportionate to its distance, but it's not moving away from us. I would just need what would be the account for why we're seeing a shift in its emission spectra. Why is that shift directly proportionate to its distance, such that the further away a galaxy is, the more shifted proportionate to that distance its emission spectra is?
Okay. I'm gonna, before I take all your time, I'm gonna let someone on if you want to interact. But thanks for interacting with me.
Yeah, no problem.
Hey, what's up, Arwen?
Hooray!
Thanks for waiting. I understand you got yourself coffee and everything. So
yeah, I'm getting all hyped up here.
Uh-oh, here we go. Now let's get into it.
I'm still here.
Hey,
right.
Okay, go for it.
No, actually, I think you're onto it. You're just like letting him show it his way, as you always do, Jimbob. So you held me off because you know I was probably gonna flat earth debate him, and now I don't wanna, because I don't know. He seemed fairly honorable for a believer in what he believes. And
well, yeah,
he's show any like terrible behaviors or anything. So yeah, cool.
Well, because I'm being nice too, and I'm not gonna. I have nothing. I don't know Leo personally, so there's nothing rhetorical.
Well, I think Jimbob was very, very respectful in our exchange. I thought that was a very respectful exchange, honestly. That's just me, though. Maybe other people disagree.
Well, Brenda disagrees. Perfect. Brenda says, oh, he's black, Jimbob, and he is 10 times smarter than you, is going to trigger you. Well, that wasn't the case.
There was actually, Jimbob, one other question I wanted to ask you. I'm not sure if this is something you might be familiar with, but are you familiar with the concepts of scientific instrumentalism versus scientific realism? Is that a philosophical category of thought? Yeah. This would be something in the philosophy of science. Not explicitly or in any depth. I mean, I could probably, if you gave me the two starting assumptions, I could probably further categorize them in something more broad. Okay. Go ahead. Well, scientific instrumentalism is the idea that our scientific theories don't necessarily reveal ontic facts about reality, that's just more an epistemic thing, where it allows us to make predictions about the way reality is and allows us to understand it, but it isn't necessarily giving us objective ontological descriptions about reality, if you know what I mean. It's not really telling us about what's actually there. It's just kind of allowing us to describe what's going on. Whereas scientific realism would say that our physical models, our scientific models, they do tell us something about what's actually there in virtue of telling us about how it behaves. And the reason I asked that is just I didn't know if maybe that was something you were familiar with, which one you might lean toward.
In a way, probably neither. In some way, depending on what we're talking about. And by your stance, it seems like you would also take the position that it's harder to, when you really get down to it, to get to actual. That doesn't mean suddenly there's epistemic nihilism about everything. But
well, no, I'm not an epistemic nihilist. I am a scientific realist. I do think our physical models tell us about the things that are objectively there. So, like, for instance, when we talk about, the geometry of space-time, whereas I think you would say, well, this is something sort of conceptual. There isn't like a thing there being bent and curved. I would say there, and again, bent and curved, that's, its own language that's not really descriptive of what's going on. Anyway, yeah, it's not very appropriate. Thank you. I would say that in virtue of being able to describe a geometry of something, there's obviously, even if we don't fully understand what it is, there is something there that has that geometry, which is why we can describe it that way. And so I was just going to say, it seems to me that you, and I could be wrong on this, it would just kind of have to be something for you to look into and kind of figure out if you fall in either camp or in neither, how you would choose to look at that. But I was going to say just really quickly that it seemed to me you might be more of like an instrumentalist.
Well, isn't it possible?
No, that's not a bad thing.
Isn't it possible to mathematically describe something that just doesn't exist at all, though?
That's going to depend on what we mean by description. So I think that we can use mathematics to quantify further mathematical structure. I think mathematics can be somewhat recursive in that sense, but I don't think when we're talking about derivatives of functions defining relations between two different sets of numbers, like say complex versus, I don't know, rational numbers or something like that, that's going to be the same as taking the derivative of a function that describes the acceleration of a car.
It just sounds like more math upon math upon math to me.
I think what Arwen's saying is also math never explains, it always describes. It can describe something accurately that's actual.
Don't you think descriptions are explanation? I would say that what it means to describe something is to explain sort of when you're describing something, at least in some like general sense, to get the discussion started at the very least, it seems that what you're doing is like predicating about that thing. So if I said I have a box here and the box is large and it's heavy and it's hot, those are attributes I'm predicating about the box, but I'm describing the box. But I would also say that in virtue of a description of the box, I'm explaining properties the box has. I'm explaining the box.
Yeah, so I mean, what I mean is that when we talk about like causal scientific stuff in regards to the general topic we're on, I would say an explanation uses descriptive language. So you could say, in a sense, an explanation is a description of something occurring and the causal relationships between one and other things. But that doesn't mean all descriptions are explanations. But I agree. I would say maybe you could get away with all explanations are descriptions in a sense. But my distinction there is math can describe something, right? I could describe a phenomenon I see, like water boiling or something. And I could describe it to high level detail using math as well as the language, as natural language. But if I were to explain it, I wouldn't appeal to math to explain it. I would actually have to get into.
But you could, though, right?
No, I couldn't use math to explain. I would have to.
I mean, but like a person could use mathematics to explain the process of water boiling. Like that's what physics does.
After you understand context, math
after the experiment, after an experiment, you could.
I guess I don't know what that.
So if I just saw water boiling and I mathematically described it, right? Mm-hmm. It doesn't give me what causes the mere explanation of it happening.
Would have to, wouldn't it?
No, if I just watch
you would
something,
have to describe. Well, how would you describe water boiling without a heat source for it? Then you wouldn't have water boiling in that instance.
Well, what does any of that have to do with math? the scientific method is descriptory. You don't actually need any
sure.
form of numbers in order to perform
Well,
an experiment.
you can't do physics if you don't have mathematics. So
That has nothing to do with it. The point is that the scientific method literally has no numbers that are
doesn't need to.
required in the process, or better more, you if there are numbers in there, it becomes dubious, it becomes risky, because usually doesn't work out. So it's just a descriptory mechanism in a very specific setup.
Well, I don't know what
Math
you mean.
is not important for this.
Scientific
Let
method.
me give an example of what our own means. Let's say someone discovers fire, and then they discover also water's making them sick, and for some weird reason they decided to start boiling the water, and then it stopped making them sick for whatever reason. Now, they didn't need math to go through the methodology.
I didn't say you need math to do this. I just said it can be done through mathematics.
I'm
that's
saying,
usually how it is done at the fundamental level.
Right. I'm saying that the fundamental difference between the two is that math, if you don't have a causal relationship through an experiment, right? And I would agree, when you start to experiment and you get into finer detail of to what extent, like let's say we need to know the temperature of water boiling or whatever, or anything else, like the amount of mercury that actually causes the effect in the body, right? There's probably some thresholds we can get to, but go ahead, Armin.
I was just thinking, can you literally describe the effect or the word cause into mathematics?
No, not in physics anyway. This
No,
really...
math, specifically, but in math.
Math. Pure mathematics doesn't really deal with notions of causality. That would be physics,
right?
But even in physics, fundamentally, notions of causality aren't to be found in the equations of motions.
Right, because you might have the impulse to say, okay, the is symbol is but that's always two ways, right? It's always going to be equal. So it doesn't work, because like causes is like a one-way effect.
Well,
so
not
you can't
early.
translate that into math.
In other words, let me get for the chat what Arun means. It's a really good point. Is that one? Let's say you said one caused two to become three. Two causing one to be three would be equal. So you couldn't, like, in other words, if you tried to make a cause.
What do you mean by cause there?
I'm saying,
before you could even describe this, you're going to need to have a theory of causation. I would just need to know what you meant by cause in that instance.
I'm saying that's why it's not possible, even if you tried to like sneak causality in math. Like,
I agree. I don't think notions of causality under any particular theory of causation mean anything in mathematics. I don't think mathematics purely deals with that.
Yeah, that's why math can explain causal. They can describe causes.
Well,
they can't explain
math can explain things when applied in a particular framework. That is what physics is. But notions of causality are not present in the physical equations. This relates to the metaphysics of causation, and where some people, like I think it might have been Russell, didn't think. Don't quote me on that because I might be wrong. I probably am. Believed that causality isn't actually a real thing because it's not found in any of the fundamental physical equations. Nima Arkani Hamed, who was a particle physicist, thinks something similar.
Really?
Yeah, he would say that causality, there is no factor or variable for causality in fundamental physical equations. So it doesn't seem that causality is really like a real thing. It's like some sort of conceptual tool humans have for like understanding the procedures of things, but it isn't like some ontically real feature of reality itself. So I'm not necessarily saying I hold this, but that is a particular way that some people may choose to look at the notion of causality.
That's not your stance that the causality doesn't exist.
Well, I'm sympathetic to it, but I wouldn't say I'm committed to it. I don't really think I have a particular notion of what causality is. So,
Well, I know it's not mathematical. That's just been established. Yet it is
Yes,
the
I would agree.
cornerstone element of the scientific method, which
I don't think it is.
therefore
I
cannot be
disagree.
purely expressed mathematically. It is a non-mathematical system. That
Yeah,
would be
I would just disagree that causality is fundamental science. I think most scientists would probably disagree with that.
it's the cornerstone of the scientific method, literally
In virtue of
cause
what?
and effect.
I don't think it is. I think that observations of phenomena and an attempt to explicate relations between states and systems that give rise to this phenomena is what science is. Now, if one wants to hash that out in causal terms, then that's on them to do so and explain what they mean by their causal terms. But I don't think that needs to be done that it's necessary for that to be hashed out in causal terms. I don't think any scientist, or at least most scientists, at least physicists and chemists, would agree with that. I don't even know if most philosophers of science would agree with that.
Well, could you cite perhaps a scientific method quotation of some kind that actually does not have the word cause in it?
What are you asking for? Like some sort of
Proof.
some
For
scientific
proof of your
occurrence?
speculation. Because
Or,
you
like,
rolled
are
that
you
out
asking?
like
Are
that.
you asking for some scientific phenomenon that occurs, but that's not generally given in causal terms?
No, not an example of a scientific experiment, a citation for the way you just transcribed your understanding of the scientific method
I didn't
without
really.
needing a cause.
I didn't really
Specifically.
transcribe an understanding of the scientific method. Look, all I said is that there aren't causal notions aren't present like intrinsically in the scientific method. The
Well,
idea
I
that
want a
causality is
citation for that
intrinsic
statement.
feature. Well, I would just reference you to the Stanford Encyclopedia of Philosophy page on the philosophy of science, on what scientific models. I think it's called science. Here, let me check. Is it called scientific models?
Okay, but the scientific method, not models, which
Well,
are
but scientific models are
based
going to be
upon
based
the scientific
on.
method. I'm
Yeah,
talking
these
about
two
the
articles
actual
right here,
method.
models in science and then
The method.
scientific representation. If you read those
No,
two
no, no.
articles, well,
Not
you got to
models,
remember
method.
you got to remember the scientific method is itself based on more fundamental metaphysical and philosophical principles. So if you want to understand what the scientific method is and understand what it's based on, you're going to have to understand what those more fundamental metaphysical principles are. And these two articles, I've read them, I think do a pretty good job of sort of outlining what science is, how it works, how things are modeled and represented in science, what the methodologies are that are utilized are. And some of them talk a little bit about notions of causality and the ontology of causality and various things in relation to science, and that these things are not necessary to scientific methodology.
All
Okay,
right.
so you're
So
are
no
you,
citation then, I guess,
I can put them
for the
in
method.
so
The
wait,
method.
so wait, Leo, are you saying that the scientific method doesn't have any necessary components or constituents to call it a scientific method properly?
No, I'm saying that I don't think that the scientific method necessitates causal notions.
Okay, so what is the scientific method then?
I think it's a way for us to
No, like
quantitatively
no, what is
understand.
it? No, but what is it? Like what's
It's a methodology.
no, but what's the method? What's the steps?
The steps in the scientific method are largely going to be preliminary hypotheses about how something works, and then running tests or experiments with a variety of changes and variables in those in the various models that are being tested to figure out which ones most parsimoniously or most accurately correspond to what it is that we're observing and measuring, to figure out which ones give the best explanations, and then continuing the same process over from that point to further hone in a meaningful and accurate and complete description of whatever system or structure it is we're trying to describe.
So wouldn't a variable
that was
itself would be
perfect.
causal? Wouldn't it be assuming you're bringing in something, and then you're going, oh, does this do the thing? And then you remove it, and then you go, oh, maybe not, and then just do it again and again. Isn't everything you just described include a causal, the variable, the independent
I
variable?
don't think so. No.
It sounds
Well,
like
relations. Wait, hold on.
Perfect,
If you both just agreed that mathematics doesn't really contain notions of causality, then you'll agree that relations between variables isn't going to be causal, because that's going to be a mathematical representation, a relation between variables.
well, no, I mean the observation isn't mathematical.
Well, of course not. But I wasn't referring to the observation. I was referring to the relation
that's
between
what
variables.
right.
Because it seemed that
No,
that's
but
what you
hold
were
on. The
getting at.
relationship between variables, it would be given by your observation of the experiment. So when you introduce a variable, before you get into math describing the thing, you would go introduce this thing, right? Let's say we had 10 people and we removed from their diet completely vitamin C, right? Completely, right? And then we saw what, I'll be charitable. What you would see first is a correlation between 9 people you took vitamin C intake, and then you would see some symptoms, and then you would probably identify the symptoms as
relation between variables.
Scurvy, right? You'd be like, oh, so to some extent, and I don't know what resolution you're arguing in as far as causality, because there might be something when you keep getting down into it. Well, then what causes the lack of vitamin C in the body to cause, and keep going, right? Keep going higher resolution. And then suddenly,
my hands are in the air on notions of causality. So, I mean, if you're going to argue that like relations between variables are going to have causal notions to them, I'm just going to need to understand what it is, particularly you're hashing out.
But don't you believe that mass and space-time, from the reference to the beginning of this, have causal relationship?
Yeah, I do. But to be honest, I don't think that I need to be capable of hashing out like some fundamental theory of causality in order to explain the idea that there's causal relations. But I do think that I
justify the claim.
I still think that I could give some like account of a causal relation there. But if you're going specifically to the notion of a causal relation, I'm not going to a specific notion of a causal relation, but it seems like you are. And if you're going to do that, then you
if you say
outline what
cause,
causal notion you're referring to.
Maybe because if you say cause, we assume you're actually mean cause, right?
Well, it depending on whether or not one's trying to examine it within causal framework. Yeah, if you're trying to examine something within a causal framework, then you're going to understand there to be causes present.
Right. So if you say space, time, and mass have a causal relationship with each other, you're using the term cause. You're not just using it like sort of like you're not swapping cause with correlation. You're actually saying, no, there is a physical interaction between things, right, of physical nature that cause
I would say there's a procedural and a counterfactual relation between the mass energy.
And what Arwen and I are saying is that in order for you to justify that assumption, you would need to do a scientific experiment that would need the actual thing you're assuming is the cause X. You need to be able to manipulate it, right? Right. So you would need. Okay, but it's not a matter of we've done it. I'm saying in the framework of what you're talking about.
You're asking me to do a thing.
Who's done it?
That thing is a thing that we have already done.
Who?
Physicists all across the globe every day.
Really? How? What was their independent variable in the experiment?
In which experiment?
The experiment to prove what you're talking about.
Well, which one? There's a myriad of them.
That mass causes the bending of space-time.
What's the independent? What's the independent variable there? Well, I with respect to what?
The observation.
What are we observation? What are we measuring? We're going to need to know what we're measuring.
Effect, right?
Understand what the independent variable is.
Okay, let me steel man what you're arguing. Mass causes the bending of space-time, right?
Well, sort of. Yeah. I guess.
Sort of, okay. Okay. Do you want to take a more local approach, like mass attracts mass, or?
Well, no. I would say that densities of mass energy geometrically curve the regions of space-time around them proportionate to the distance of the point in space-time to the mass energy density.
So Arwen's asking, what was the first? What was the observation? Second, what was the independent variable?
We can observe the gravitational lensing of light.
But doesn't that,
and we can observe it proportional to the mass energy density of the galactic clusters through which it's moving. The more mass energy density, the greater the lensing.
So gravitational lensing of light is the independent variable, or the
I don't.
effect?
I'm.
How
Not to
did
be
you
rude, but I'm not
manipulate
sure
it
that you
within the
understand what an
experiment?
independent variable is.
Independent
I
variable
need
is the thing that you're saying is causal, such that you could have access to it, manipulate
I
it,
don't.
introduce
I
it,
don't know
and
what
remove
that
it.
means.
It is the cause of the
I don't.
effect. You need to manipulate it as the experimenter, physically, provably, in order to establish whether it
I
is the
I don't know what
cause of
I
the
don't know what that
presumed
means.
effect.
I don't know what that means. An independent variable is just
I'm,
is a
I'm
variable.
not
Is a
talking
variable,
difficult
but
here.
the variation is not. It doesn't depend on any other variables. It's an independent. Its variation is
Other variable. No, it's just what it's called. That's literally what
yeah.
it's called.
That's what I'm
Independent
saying. Is that
variable.
an
It's
independent? That's why
because
I'm
there are
understanding
other
where
variables.
you keep saying
Yes, there are,
cause,
but they're
because
not
causality
involved
doesn't.
within the
You
experiment.
control
It has
it.
to be precise. You have to have one independent
I don't know
variable that,
what.
as the experimenter, you are
Wait,
going to
wait a
manipulate.
second, Leo. Are you really saying that in the scientific experiment, like the way we all learn it, the scientific method, you don't know what the reference of the independent variable is when you
No,
introduce
I'm
the
saying
thing?
that we keep using this word, but I don't think it means what you guys think it means.
Independent. It means it's
An
not
independent variable is a
non-dependent.
variable that doesn't change based on other variables. It's an independent variable.
Yeah, you're not
That's
changing
all.
that.
That's all an
What
independent
does that
variable
have
is.
to do with non-changingness that you seem to be
What, wait,
making?
do you know what the term variable means?
Yes,
It
variation.
means you
Yeah.
introduce the same thing, right? That's not the thing that's changing. You keep
And so
introducing that thing.
what does independent mean? Not
It means
dependent on other things.
Isolated. It's
So
another word for isolated.
it's its
variable
own.
means changes and independent means not with respect to other things, then
Mhm.
independent variable are variables that change not with respect to other things.
Okay, yeah, let me explain this to you. So if we take 10 people, we'll use something more drastic. Introduce the independent variable
I
of
don't know why we're
liquid.
getting hung up on
Hold
independent.
on,
I
hold on.
honestly,
Why
I
is
mean,
it?
you can
Just
explain it. I
trying to
just don't think
clarify
Okay,
here.
concept
Just
of
just hold on a
independent
second.
variables is
Hold on a
really
second.
relevant here. But you
Hold on.
can, I mean, you can explain it if you
Well,
want
we're
to.
talking
trying
about
to
the scientific
clarify what
method.
we're talking about.
Yeah. So if you introduce what we call the independent variable mercury and introduce it to bodies, human bodies in some way, orally, um, let's say 30 people, right? You introduce this to them, and this is the independent variable. Now they all have different controls. Let's say you control their diet, their weight. Let's say we have a sample of weight, male and female, whatever you want. You can set what those are. Now the independent variable is going to be the assumed cause, the assumed effect. So the thing, the dependent variable, the thing that depends on the independent variable to do something to it. So if you introduce the independent variable, mercury, it's independent. It means it itself is not changing, right? You don't do anything to it. You have it isolated independently from the rest of the things. You introduce this thing into this other system called a human body, and you go, well, shit, everyone's getting sick from this. Let's test this again. Unfortunately for the sample, they're going to have to ingest a bunch of mercury and get really sick. You're establishing a causal relation between ingesting mercury, right? That is the thing you're introducing, right? So you're not, when you say that's what else would you refer to an independent variable in a scientific method? What else would it be other than the thing that you're introducing as the assumed cause? I mean, is there any other thing it could be?
I'm not sure what relevance this has to the discussion.
Is because when you establish space, like mass causes bendy space time or whatever it is, right? When you assume that, you're making a causal
really
claim in physics, right?
That's actually something we've observed and we use every day to make predictions to come true all the time.
I know. So predictions are not.
Are you saying that? Are you saying that? Well, they kind of they
don't. You just
are
argued
you
they
saying?
don't.
Are you saying that models that make predictions consistently and repeatedly aren't good models?
They could be good in if you're measuring good by predictive, but you can have false models predicting.
Well, yeah, but we don't have false models that consistently predict a wide array of things within a specific framework.
Yeah, you could have no. You could
And
totally.
if a model did that, then we wouldn't expect it to be false.
Yeah, you can
You're
have
talking about what is establishing tests, right? That's not experimentation. That's not science.
A model is the
Science will prove
absence
the
of an
cause of an
experiment.
effect. If you want to establish what is or make a measurement and just establish metrics about something, that's not science.
Leo,
That's
do you
Well,
think
yes,
a
it is.
model is an
information.
adequate replacement for an experiment?
Wait, that makes no sense. Models are based on experiments.
Okay, so you do need an experiment.
Of course, how do we learn things?
Learn what things? Causal things?
Anything.
No, causal things. What's an experiment for if not establishing a causal relationship between things?
You
To
seem to be
understand
talking
things. So
about a
you don't
measure.
need to use causal language.
You're just talking about measuring
So
something.
what are you
That's not
learning?
an
Yeah.
experiment.
Wait. Well, actually, that's literally what experiments do. They measure things. So that we can
No,
figure out whether or not our models predicted those measurements, and the ones that most closely predicted them are probably the most accurate.
that's called testing a model. That's
Yeah,
not an
that's literally
experiment.
what science does. Science
No,
forms
that's
models,
not
and
what
then
science
yes,
does. Science
it is.
established the cause
It
and
forms
effect through
models. It forms
experimentation
models, and
using
then
a
it tests
scientific
them,
model.
and then it tests those models to figure out whether or not they make predictions about the way things work. The more accurate that their predictions are, the better the models are. That's literally what scientists do every single day.
So if I observe a dresser and I measure it from a model I have in my head and I have a hypothesis and I go, it's probably about 4 feet. When I measure the dresser, am I doing a scientific method by measuring the dresser?
Yeah, you're saying, okay, my prediction is that this dresser is going to be 4 feet tall. So let me measure the height of the dresser to establish whether or not the measurement of the dresser actually corresponds with the prediction that I am making. Now, you might have a set of priors or some sort of prior model that prescribes this 4-foot prediction, and say you measure it and it comes out to 50 inches. Well, I would say your model was pretty accurate because 4 feet is 48 inches. So that's a very reasonable measurement, one which I would say concords with your model that the dresser is 4 feet tall. Would you not agree?
Well, the question is
Nice
whether
measurement.
that's
Well, no. Do you agree with what I said or not?
Well, you measured it up pretty well.
I would
but
imagine
this method
I would
is-
say what you said is I looked at something, I made a guess of the height, and then I verified whether my guess was correct about the height. That's what happened.
Yeah, that's what science does.
I'm saying is that
let's measure it and see if
I'm
that's
asking if that's an adequate replacement for an experiment.
true. Well, that is an experiment.
Is it an adequate replacement for an experiment?
Well, no, that what I just described is an experiment.
So what was the viable hypothesis?
The hypothesis was that the dresser was 4 feet or 48 inches tall.
And so I didn't need an independent variable to
I see you keep getting come on independently. We don't need to talk about that when we talk about scientific models.
method.
Well, that's what scientific models are. They're based on the method. They're based on the methodology.
What you just
scientific
said,
models utilize experiments that are based on the methodologies we have established in the philosophy of science. Yes.
What you just said is you don't need to you don't need a viable a hypothesis with an independent variable to do a scientific experiment.
That's not what I said. I said is that the language of dependent and independent variables isn't going to be relevant to every discussion about scientific experiments or scientific hypotheses.
Okay, so if I guess the amount of gumballs in the machine,
just for reference, the independent variable in the example I gave would be whatever the height of the dresser is. And then
so is buying a lotto ticket a scientific experiment?
And then what you're going to do is you're going to see how closely the dependent variable matches up with the independent variable.
Is winning a lottery by guessing the numbers of the lottery doing a scientific experiment?
No.
Why? How is it different than guessing
the height? Because you're not making a hypothesis.
I'm not making a hypothesis if I guess the numbers of the... Why, how is that not a hypothesis if guessing the height of something is...
Randomly guessing something about something else isn't necessarily making a hypothesis. Saying I have this physical thing and what I think I am hypothesizing about this physical thing, that it has this particular physical parameter, and now I am going to measure the physical thing to see if my prediction about the parameter that it has with respect to what I'm measuring is in fact true. That's different than I'm just going to guess some numbers because I want to win money. Like these are not synonymous scenarios.
I feel like they're just guesses and you're either right or wrong.
Well, hypothesis is a guess in like a fifth grade understanding of hypothesis, but like that's not really what it is like in a graduate level.
So what does a viable hypothesis mean to you though? Then
a viable hypothesis is something that is supposed to be the case that may or may not be true, but that reasonably fits with current models related to the same specialized field.
So I can have a viable hypothesis that a shoe is a shoe?
So, for instance, eternal inflation is a viable hypothesis in cosmology, but we don't know if it's true or not. It fits with the models, it fits with the mathematics, but we don't know if it's actually true. It's viable.
Okay.
Sorry. I'm cracking up here.
Okay. Yeah.
Just for the record, cracking up isn't a viable response, no pun intended, to an argument.
Well, everything you're talking about sounds really fascinating, and yeah, I'm sure it's been very interesting to think like that and to
guessing the lottery numbers based on
action.
Nothing. Yeah, no, it's not based on nothing.
Categorizing your actions as science, but it has actually nothing to do with science.
I don't actually think I'm
investigating the world.
My act
testing.
Testing
and investigating the world.
To describe what scientific methodology is actually rooted in.
Masturbator, guessing the lottery numbers is based on probability. You could have a lottery that doesn't have a billion potential outcomes, and it's still a lottery, and it would be based on probability. So it's not based on nothing.
Well, the outcome is based on probability. I don't think the guessing necessarily is.
Well, guessing is an assumption of outcome.
What?
Guessing is a supposed outcome.
I guess I don't really understand what that means.
If winning the lottery, a set of numbers, is an outcome, then making a guess on those numbers is a supposition of a potential outcome.
So sure, yeah.
So,
I mean, I guess that's just entailed there, so I don't see why that's profound.
Well, I'm just saying it would be a viable hypothesis, and you'd be doing science under your.
I don't. No,
standard.
no, we wouldn't.
Guessing someone's shoe size.
That's not a scientific experiment.
But guessing
Why
the
not?
height. Guessing
Why
the height
not?
of a dresser is.
Just well, you
According
didn't
to
guess.
your
You didn't.
system,
You
why
didn't
not?
just guess the height of a dresser.
I didn't just guess the shoe size then.
No,
What do you mean?
I mean, perhaps you didn't. Perhaps you have some sort of model or some prior set of reasons for supposing that somebody's shoe size is a certain way, and you're curious to know whether or not that was an accurate way of arriving at their shoe size, and the way to do that is to measure their shoe size. But that's different than just blindly guessing what their shoe size is out of the blue. If that's not based on some set of priors or some model that you're using, then it's not going to be science. Just guessing things isn't science. It's prescriptions about particular values for parameters given some prior model or set of priors. I mean, this is going to depend on certain statistical models that you want to use. Most use Bayesianism, but so you're going to, priors and conditionalization and all sorts of things like that. But yeah, just like randomly guessing things is not science.
Okay, so it is science without the scientific method, but also if it's about shoes, I guess you don't like it anymore, and then it's not science because it's just a describing of measuring things exactly like I said.
I don't
So
know what that means.
what
So
determines the border between it being science
Right.
and then just measuring stuff?
Right.
What's the difference?
Yeah. What's the difference between measuring something, even if you
Well,
don't-
are the measurements that you're making with the intent of confirming predictions made by some prior
Okay,
model?
here's a question. If I just measure a dresser without guessing it, am I doing science?
If you just say, all right, I'm just going to measure how high this dresser is.
Mhm.
No, you're not doing science.
But if I
Isn't
guess
shoe
it,
size a model on its own?
What do you mean by guess it?
but if I get, okay, so
Are you
you're
saying, all right, this
Hold on.
dresser's 6 feet tall?
Hold on, let me just
It's obviously like not that even remotely that tall. You just threw that number out as a guess. That's not science.
let me just summarize what you said. If I look at my dresser in front of me and I go, based on my prior knowledge, my height, I'm sitting, I'm going to guess 4 feet, right? And then I go measure it and I'm right. You just said I just did science. But if I just don't guess and I just go and I just like walk right on my way to the bathroom, I have a tape measure on my belt and I just measure the thing. It's not science merely because I just didn't take a guess.
What's that?
You're saying if I just measure something without guessing, I'm doing the same actions, right? I'm not. That's not science.
I don't think so.
Okay.
I don't think you're doing the same actions.
I'm not just measuring the
Just
thing.
measuring something because you're like, how
Yeah.
tall is this? Let me measure it. That's not science. But saying, all right, I have reasons to suppose that this thing may be this tall, and I'm going to measure it to see if those reasons are accurate in the prescription that they've given for the height of this object. So let me measure it and find out. Yeah, that's kind of something.
How about testing your model of shoe size, and you're looking at it and you're like, yeah, I think it's that shoe size because I've dealt with this model before. So why isn't that
That would be
science
science.
then?
That would be science. Yeah. If you're
Oh,
working
so
from
now
a
it
model,
is
and the model gives predictions about something, and then you test the thing that you're making predictions about to see if the predictions come true. Yeah, that's science.
Okay.
Okay, so as long as you make a guess and then measure it, it's science. But if I just measure it because I'm just maybe collecting the wide variety of heights, let's say, of random dressers, I just have this like weird impulse when I see a dresser, I measure it, and I'm just always doing that, and I keep a
Are you
catalog.
compiling the data for a reason? Or like, are you trying to determine what average dresser height in the American household? I don't even know if you live in America, but let's just say, are you trying to like
No,
determine what like the collect or what the average like dresser height of the American household is, or are you just doing
No.
this because it's like
I'm what I'm doing is I'm seeing how many dresser heights I can accumulate in my lifetime.
you're just doing it to see how many dressers you can measure in your life?
Right. Yeah. Is that science?
I don't think so. No.
But if I guess how many I can accumulate in my life, then it's science.
Simplicator. No.
Okay.
Now, if you had a model that was going to give, like if you said, well, the amount of time that it takes to measure a dresser on average is this, there's this much time in a day, the average lifespan is this, and based on all this prior information, I'm developing a model that says that based on all that, I should be able to measure. I'm just going to use random numbers here. So I should be able to measure 5,000 dressers in my lifetime. So I'm going to measure as many dressers as I possibly can in my life to see if I get to 5,000. Then yes, that would be a scientific experiment.
Well, there's.
I think the fundamental thing that you guys are missing here is that there has to be a model prescribing predictions against which you're testing the thing that it is that the predictions were made about. Just measuring something isn't science. Just randomly pulling guesses out of your ass and seeing if you're right is not science. Having a prior model that prescribes values for parameters or what have you, and then testing things to see if these parameters are accurate, now that is science.
Yeah,
Okay,
so how about dress size models? Because I've actually known somebody that makes custom-made clothes, and they have like this amazing size system. It's you can even you can make a map of it. It's fascinating, right? It's a dress size model. So why then isn't this scientific either? Because they've been very scientific about it.
Are you asking me if making people's clothes is science? No, making people's clothes is not science.
Okay.
Now it isn't. But shoes. Shoes was science, but clothes isn't.
Making shoes, I don't think that's I mean, well, it depends on what you mean by science. Everybody could say there's a science to making shoes or there's a science to making clothes, but do they mean science in the sense of like actually doing an experiment in a lab? No, I don't think so.
Well, I'm just bringing it up because you said that it is like can become science if there's some kind of model involved in the anticipation of what you're dealing with. And well, dress sizes have models. So I thought, okay, isn't that then scientific according to your standard?
Dress sizes have models? I don't think I understand what that means.
Dress sizes. You were talking about dress situations.
I was talking about dressers.
Didn't he?
Dressers.
Yeah, we're just talking past each other. Okay, one last example.
Actually, I don't think so.
What is the model I'm using such that I can guess the dresser the height and then I go measure it, right? Like, and if I did have a model, if there was someone next to me who was also just guessing the height of the dresser, right? Just based on their own mental model. Let's say it's mental modeling, their memory of dressers and heights, their memory of heights relative to their position. And they kind of assess it and they go, I'm going to guess 48. And I guess 48 and we're both right. So which one's doing science? If they have
Well, I'm
two,
sorry. Can you? I don't think I was following.
okay.
that.
If I guess if I guess a dresser size, right? I guess I look over at my dresser and I guess the size,
Mhm.
and I'm right. You said that's science because I
Well,
made
no,
Okay, you said it was before.
no, I didn't.
Okay, I think you did, but maybe you didn't mean it.
Well, I didn't say that was right. No.
Okay. So science would require some modeling. So in that sense, you couldn't just take one instance of making a hypothesis about the dresser's height and then measuring.
Being right about guesses you make is not what science is.
But if your modeling is just your brain's ability to guess correctly, you're modeling, right?
I think you mean something different by model than what I mean. When I say
Some
model, I'm talking about like a theoretical model that is based in, at least in like, when we're talking like physics or chemistry or something like that, we're going to be talking like, we're going to need dynamical variables, we're going to need equations of motion, and we're going to be able to derive predictions from them.
Okay, I'll ask you this last, and then I'm actually half hour over. I really appreciate your time, Leo. But
Okay.
let's say, can you model something in your head? Like, there are people who are really good at actually.
Yes, but that's not what I mean by model.
Okay, so that doesn't count as a model, even though it's based on
not
a lot of
in
information.
The sense of science. No, that I would not consider modeling things like somebody modeling something in their head in like some metaphysical or philosophical or epistemic or what have you, whatever sense you want to use. I would not consider that modeling the way that things are modeled in science, where they're based on a set of like prior conditionals. They're based on dynamical variables, equations of motion, other prior probabilities could factor into this. All of these coming together to form a model from which predictions are derived, in a sense that when you put all these things together, the amalgam of them says, yeah, you should see this. And so we go out and we say, all right, is this a thing that we can actually see under the set of conditions that this model is telling us we'll see it? If yes, okay, the model is accurate. If no, well, then either the model is inaccurate or maybe some parts of it are accurate and some parts need to be revised, whatever it may be. But
Okay,
being right or wrong isn't what makes it science.
Okay, so with the dresser, what is the viable model that would make that a scientific experiment?
The model would be, look, okay, so I know from like looking online and walking in stores and stuff that the average dresser height is about 5.5 feet.
Probabilistic.
So what I'm wondering is if this dresser here in my buddy's house is 5.5 feet tall. You know what? 5.5 feet would be 66 inches, I believe. So I'm gonna guess.
About a standard model?
I'm gonna guess, and I think I'll guess 63 inches on this. And I grab a tape measure then. So I've got a model. The model is that I have a prior about the average size of a dresser in a house. This factors into the model. And so what I'm wanting to know is whether or not the house that I am in, if this dresser in that house concords, or rather comports with that standard, that average, that prior that I'm using. Because like I said, in a Bayesian sense, you work with priors in scientific modeling. And so I grab a tape measure, I do an experiment by measuring the dresser, and it comes out to, let's say it comes out to 62 inches. Now I guessed 63, so it was an inch below that. So my guess was accurate. The prediction that I derived from my model was that it'll be, let's say 62 inches was accurate. The average is 66 inches, and I would say 62 inches is it's reasonably close to that. I would also say that's accurate. So you would say that your model provided an accurate prediction for the height of the dresser in this person's house based on the priors that you were using to formulate the model.
And you would call that whole thing. Hold on, Arwen. You would call that whole thing as the scientific method.
Yeah, I would say you just did science there. Yes.
But did science or the scientific method?
I don't draw a distinction between them.
Okay.
You don't? Okay.
No. Doing science is using the scientific methodologies that we have. Yes.
Okay. Anything else, Arwen?
I don't know. I'm kind of lost at this point. It's hilarious though, but yeah. No, look, all these things that's just measuring something, and yeah, things that are man-made, like a dresser. I get it now. You weren't talking about dresses, but about a piece of furniture. I get that now. It's still based on a model. I mean, the person that's going to craft
Yes,
that
of course.
isn't just going to randomly like construct something out of wood. And because usually when you do that, it doesn't fit. Well, the pieces don't fit, so you need a model. You need a design, right? But that doesn't make it scientific. It makes it, perhaps you could say, applied sciences, or another word,
Which is science.
a
Applied
piece of
science, literally
engineering.
science. Engineering is science.
Engineering. No, it isn't.
Engineering is also science.
No, it isn't. Science is method.
Okay.
Engineering is engineering.
Engineering, I would say.
Engineering is a science. Yes, engineering is
No,
science.
it's defined officially as applied sciences,
Which
not
is
science.
applied science is science. Wait, hold on. So is applied psychology still psychology? Is applied economics still economics?
I don't know. There's no specified
Is
classification
applied
for
physics
those
still
things.
physics?
There's no fields for those specific things, but yet there is applied sciences, also known as engineering.
So-
There is
Which
a
is
classification. That's official. It's built in the language.
So Leo, you would then say that math is science, right?
no.
Okay, you wouldn't say math is science.
I would say math is integral to doing science, but I
Okay.
wouldn't say math
But-
is.
okay, so the
identical to
process of doing math isn't science.
No, the process of doing science involves math, but the process of math is not a science.
Okay. Yeah, I think that people do make the distinction, the scientific method, science in general, to engineering, because engineering you can do based on just law and observation of law. And
You
so
can do the same thing in science too. It's called theoretical physics.
right, but you could like, for instance, before any sort of scientific methodology, you could, by trial and error alone, establish some engineering based on law. But
Well, yeah, but that's just experimental science.
right, but no,
Doing experiments to establish something or to develop a technology, that's experimental science.
right, but you could engineer based on law alone and
Yeah,
no
that's
scientific
theoretical
explanation.
science.
No, that's engineering.
That's actual
No,
engineering.
That's
Yes.
theoretical science. If you're not
Those
doing like actual
departments are
experiments,
called
but you're just working
engineering.
on like theory and models and things like that, then that's theoretical science. If you're actually doing experiments in a laboratory, you're actually conducting experiments, and that's experimental science.
Well, that's where things actually happen, right?
There's a difference between experimentation and theoretization. But both are very important to science. You have experimental physicists, you have theoretical physicists. You have experimental psychologists,
I know.
you have theoretical
I've seen the Big
psychologists.
Bang Theory. Theoretical physicists make up shit and bluff people, and then if you're
Well, the
lucky,
Big Bang isn't
somebody's
made up.
interested, or there's some kind of industrial application or mental modification that could be tapped out of it, then you might get an engineer to actually try to help you prove your shit. Yeah, that's how it
Well,
works.
I don't really understand that, but
Just
Yeah, it
watch
seems
the
like
Big
we
Bang
just-
Theory. They literally show you what happens.
what are you talking about? Like a TV show? Why would I watch a sitcom? Like that's not.
Because
Wait,
it's
you,
about a
you get
theoretical physicist.
you get your
and
science.
it's
You get
pretty
your science
accurate.
from a sitcom. You get your science
I've
from
known people that are exactly like that
you get your science from a
in my
sitcom.
real life.
You don't read textbooks. You don't watch lectures. You
Oh,
watch.
but I have met actual theoretical physicists, and they are kind of like that.
Like
they
who?
They hate that character because they are actually kind of like that.
I don't know what you're talking about. Anyway, that's I mean,
Yeah,
appeals
I know
to
you don't. I do.
appeals to personal testimony don't really matter to me, if I'm being honest.
All right, guys, I gotta wrap this up. I'm 42 minutes over my normal time. But thanks, Leo. Thanks, Arwen. And Leo, you're welcome anytime. Another topic that suits you, you want to jump on, please do.
Sounds good, my friend.
Cool. Thanks, Leo.
Subscribe.
First.